Hey y'all! Today we are going to talk about linear versus non-linear lines. I would like for you to go ahead, if you're taking notes with me, get a piece of paper out, and I know I have a lot of information on this right now, so grab a pencil, your colored pens, whatever you use, and go ahead and set up your paper. So hit pause, set up your paper real quick. All right, hopefully you have your paper ready. So the first thing that I'm going to do is I'm going to give you some tips on linear and non-linear. I want you to always remember that linear has the word line in it. Line, R. Linear, L-I-N-E, linear. So a linear line is a straight line and it is constant. That's the first thing that you need to write down for your tips. A straight line. Straight line, and it is constant. Okay, well, what does constant mean? Constant means it's continual. It's always doing the exact same thing. It's never changing, ever, ever, ever. It always stays the same. So, linear, a straight line, and it is constant. Well, what would a non-linear line be qualified as then? So a non-linear line is going to be obviously not a straight line, so it's not straight, which means it can have curves in it. All right, so we can put that out beside it. It can have curves in it. It is not constant, so that means it is changing. So, a linear line is a straight line and it's always constant. A non-linear line is not straight, which means it has curves in it, and it's not constant, it's changing. So, let's look at a few equations and remind ourselves of what is linear and what is non-linear when we look at particular equations that are given to us on work questions. So, if you have an equation that is y equals 3x plus 4, this would be considered linear because my starting point is 4, and every single time my line is going to have a growth of 3. It's going to always constantly change by a growth of 3. There's nothing crazy going on in this equation. So this is linear. It is okay. It is a good equation. It's linear. So let's look at another equation. What if we have y equals x squared plus 5? This would be nonlinear because that square right there. So nonlinear. And I hope you remember what the 2 makes. A baby 2 makes the shape of U. So this would be a parabola. When you graph this out, it's going to have a U shape. Always, always, always. So that is not linear. Anytime you have any exponents at all, it's going to be not linear. So what if I had the exact same equation, y equals x to the 3rd power plus 5? That 3, that exponent, that's going to make this non-linear. And if you remember from teaching, our exponent 3 creates a weird looking S shape. It's going to create a curve. So anytime you have exponents with your x, it is non-linear. There's also another one that we can go over. What about y equals the absolute value of x plus 3? Anytime you have absolute value bars, those absolute value bars snap together and they make the shape V. So that is non-linear. So anytime you have an exponent, it's nonlinear. And anytime you have those absolute value bars, they snap together and make the shape of V. That is also nonlinear. Other examples of nonlinear equations would be y equals 2 over x plus 3. The reason this equation is nonlinear is because that x is in the denominator. Anytime the x is in the denominator, it is non-linear. But it is okay if x is in the numerator. So if you have y equals x over 2 plus 3, that is okay. That's linear because the x is in the numerator spot. That is okay. So let's recap these real quick before we move on to tables. Anytime we are working with exponents, it is going to be nonlinear as long as that exponent is with our x. If we have absolute value bars, nonlinear. If the x is in the denominator, nonlinear. So I'm going to highlight the linear equations in this particular section. So the linear equations would be y equals 3x plus 4, that is okay. And y equals x over 2 plus 3. Those are linear. All right, so let's move on to some tables. Go ahead, hit pause if you need to, and set up your tables. We're going to do sideways tables, and we're going to go back and review how we can determine if something is linear or nonlinear when they only give us a table. You might remember how to pull the equation out of a table. Then you can just go back to these different equation reminders that I'm showing you to determine if it is linear or not. Otherwise, we need to determine if the table is constant or not. What is going on in the table? So you can create, whenever you don't have enough room, you can create a sideways table. So let's put several little lines in there and make a few boxes. Let's go ahead and do 2 examples. We're going to do a linear and a nonlinear example. Draw that out. Draw you a few spots to have some information in there. Okay, so let's fill this in. You know, if you're in my classroom, you know, obviously I've got to change colors. I've got to make this a little bit colorful. Have some fun with it. So let's start out with the first problem. I'm going to go back to a linear example. So y equals 3x plus 4. So if I have 0, let's say 1, 2, 3, 4, and 5. So obviously my starting point is 4. And every time I'm going up by 3. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. All right, so looking at this example, how would we actually determine if we weren't sure and we weren't creating this with the teacher? How would we determine if this is linear or not? You need to create little bubbles on your triangle. So have a little bubble between every single x value and between every single y value. That's called the change in y over the change in x. And anytime you do the change in y over the change in x, that's going to give you your slope, and that'll be in another video. But in order to determine if something is linear or nonlinear, you have to use this change and see if it's constant or not. Is it continuing to do the exact same thing every single time? So 0 to 1 is plus 1, 1 to 2 is plus 1, 2 to 3 is plus 1, 3 to 4 is plus 1, 4 to 5 is plus 1, 4 to 7, plus 3, 7 to 10, plus 3, 10 to 13, plus 3, 13 to 16, plus 3, 16 to 19, plus 3. So the change in y, is it the same every single time? Yes. The change in x, 1. Every single time, the change was the same. It added 3 every single time that it added 1 on the top. So this would be considered a linear table. So I'm going to go ahead and highlight that because anything that I have that is linear on this particular notes page is getting highlighted. So it goes back up with my tips at the top. All right, let's do another example. Obviously, I want this one to be nonlinear, so it's going to take a second to think about what's happening here. I'm going to put some numbers in, and I want to go over those numbers with you without telling what's happening every single time. All right, so I put 0, 2, 4, 6, 8, and 10 at the top. On the bottom, I'm going to put 4, 8, 9, 10, 12, and 18. All right, so now we need to do the exact same thing. We need to do the change in y over the change in x to see, is this table constant? Is it constantly doing the exact same thing every single time? So I'm going to create my little bubbles between each item in my table. 0 to 2 is plus 2. 2 to 4 is plus 2. 4 to 6 is plus 2. 6 to 8 is plus 2. And 8 to 10 is plus 2. Let's see, is the same thing happening in the y area every single time? And if it is, it's linear. If it has a not constant growth, it is nonlinear. So 4 to get to 8 is plus 4. 8 to get to 9, that's going to be plus 1. So I already know something's off. 9 to get to 10 is plus 1. Okay, it goes back. 10 to get to 12, no, that's plus 2. And 12 to get to 18, well, that's plus 6. Because my x at the top was plus 2 every single time, the bottom needed, on the y values, needed to have an exact increase every single time to be linear. 4 over 2 is not the same thing as 1 over 2. 1 over 2, those would line up, but the entire table needs to be correct. 2 over 2 and 6 over 2. All of those things would be different. So 4 over 2, then 1 over 2, then another 1 over 2, then a 2 over 2, and then a 6 over 2. That's my change in y over my change in x. Because those are different the entire time, this would be non-linear. It is not constant. It's changing way too much. It's changing. And when you graph it out, it would have curves. Okay, so our last thing that we're going to go over is we are going to, I went ahead and pre-made a few graphs, and you can just follow along with me and create your graphs later. So I have one graph I'm going to tape in here, and I have another graph that I created. I'm going to tape in over here. And let's go over these graphs. So if I am given a graph and my paper that I'm working on or my question that I'm working on ask, is it linear or is it nonlinear? Don't judge by just looking at the graph and quickly stating, oh, this one looks straight, this one looks crooked. You can do that if it's extremely obvious. But what if this person was just driving down the road and it was kind of bumpy as they were drawing that one? You need to determine, how can you prove that it is nonlinear? So in order to prove that something is nonlinear, you've got to find that change. How do you find a change on a graph? Well, you need to do your growth triangles, your rise over run, rise over run. And if it's constant the entire time, you will then know, hey, this is constant, it's not changing, it is not curved, it is a perfect straight line, it's linear. If it's changing, if it has curves, if the growth is not constant, it is obviously not linear. Let's go over these two and figure out if it's linear or nonlinear. So going from one lattice point to another lattice point, we're going to rise 2, run 1. Rise 2, run 1. Rise 2, run 1. Rise 2, run 1. And obviously you can see that this is linear. It's perfect. Every single time the rate of change is constant. So this would be linear. And obviously with all of my examples on this paper, I'm going back to the top. Anytime something is linear, I'm highlighting it. So this is linear. This is a great line. It's perfect. It's straight every single time. The increase is the same. It's not changing. How can we determine, that was my dog, he came in the room, excuse me. How can we determine if this line is linear or not linear? You need to check from lattice point to lattice point. What is happening? It's okay, bud. Hold on. What's happening every single time? So from lattice point to lattice point, draw your growth triangles. How much up? How much over? How much up? How much over? So